Okay, we have finished regarding the battery. It's a very important point and a key parameters, economical parameter for autonomous PV central, because it's usually as soon as you had some battery, the investment payback time is very long, okay, compared to PV central, which is directly connected on the grid. As I told you yesterday, the price of PV has considerably decreased the last 10 years, divided by more than 10 in 10 years. So now a PV panels is very cheap compared to 10 years ago. But the main price of autonomous central now is mainly focusing on battery, because of course the battery price didn't change so much. We need a lot of battery for phone, for car now. So there is high level of demand on the battery. So the number of cycles that will be allowed will depend on the depth of the discharge. And so what is important, so with the battery, you can directly connect PV modules on the battery in artisanal small powered system. It is okay, but I strongly advise to take a charge and discharge controller between the battery and the PV central. That will avoid some problem of fluctuation, avoid also some problem of, for example, if big difference between power production, and so it's very important. Okay, so the efficiency of battery charge is quite good. But there is efficiency, as I told you since the beginning. As soon as you are converting, changing, you are losing. So the efficiency of classical battery charge now is around 80%. Okay, but you are losing a bit when you are charging and discharging. So you can imagine if you had 80% of efficiency regarding the charge, and you use only 80% of the capacity, you have to multiply twice by 80%. So to increase the real battery that you will buy. Okay, we will see that on a tutorial. Okay, so if you had also an MPPT regulator, you can win energy. Of course, as I told you, it will focus on the maximum power production of PV. And for this, you will have efficiency battery charge, global efficiency charge of 80%. Compared to the fact if you don't had maximum power tracking. But now most of the discharge and charge controller that are designed for battery for solar application are including MPP tracker. It's okay. So what we can is to improve the last time of, especially its lead acid battery. There is some lithium batteries that are used in some application, but it's very expensive compared to lead acid battery. So it's still the standard we found for typical autonomous installation. So we have to avoid large discharge current. To avoid large charge current, so intensity is it could be high intensity is a problem. to avoid deep overcharge level. Okay, so when if the battery charge, you have to disconnect. Okay, so it is the role of the discharge and charger controller to disconnect, to avoid to inject, to continue to inject some current in the battery when it's full. That is the reason why when you don't put a discharge and charger between PV and battery, it could be a problem to damage the battery when you directly plug some PV panels on the battery. Of course, you have to avoid deep under discharge level. Okay, so the depth of discharge over 80% is dangerous in terms of number of cycles. You have seen it's not linear, so when you are going deeper than 80%, the lifetime is considerably reduced. To store, if possible, when it's fully charged, okay, and operating temperature between 10 and 20 degrees is good for the battery. So finally, you see, the battery and the PV modules have the same challenge in terms of temperature. So PV don't like too much high level of temperature because the efficiency and the aging is increasing, the efficiency is decreasing. It's the same for the battery. So could be a problem for battery for autonomous installation in Africa, for example, where the level of temperature could be high. For the battery, the lifetime of the battery is decreasing also with the temperature. Okay, so you can have a design of a battery rack for, and you estimate that the lifetime will be 9 years old, and for sure if they operate every day around 30 degrees, you will have to change some battery before the 9 years. Not all maybe, but some will aging and will be destroyed. So it's very important. So in very, very hot country, the battery rack are stored in a cooling chamber. So it's a paradox because you are generating electricity and a part is used to cool down your system. But it's the same for the inverter. When the inverter is submitted to it's electronic, so they don't like to operate at high temperature like your computer. So if it is too hot, extreme condition, usually battery and inverter are in cooled chamber. Okay, so part of electricity which is generated is injected to cool down some critical elements and especially electronics components. So during use, it's generally good if you don't discharge more than 20% per day, but of course you can't take this assumption for designing your system, because that means if you just take this assumption that you will only use 20% of the battery capacity, the price will completely explode. So usually you said that you will not use more than 80 or 50% of the capacity to design. But it's better if during the classical day it's around 20% a day. So you see, it's very also delicate component, the battery. It's expensive. The lifetime is not so high compared to lifetime of PV modules, and you don't like extreme operating condition, extreme taking a lot of electricity inside and also temperature. Okay, you can have also problem of fire You have seen, I think, a lot of things regarding electrical car. And there is nothing to do when there is a fire of battery, just wait that is finished. It's also new training for the fireman for PV installation, autonomous PV installation or electrical car, to manage when there is a fire of a battery. Okay, really, so the fire, there is some precaution to take. So there is an international standard that said that you, so it's international, you have to be able to disconnect the generator to the inverter. And so it has to be able to be accessible from external part to cut it. So some example how we will proceed to design. So the more complicated is the autonomous, because it is for autonomous installation that you have the, as I previously present, most of modularity, which is possible, most of components that are possible to design, and so you have to choose. So the methodology is first to identify the electrical energy which is required per day. Okay, so we will estimate that in kilowatt-hour per day. Usually you have a security coefficient. Okay, you can measure by 20% this, you know, as a first ROS approach to have an idea. Okay, you don't, if by any chance, if it is for a building and you had you plug your some smartphones and you didn't consider that on your estimation of energy, it's a bit stupid. So generally you measure this energy. You have to identify where you are, of course, and the estimation of the solar radiation that will arrive per month on the PV system. Okay, so in kilowatt-hour per square meter. Then, thanks to that, you will be able to size your PV central. Okay. That have to bring the energy which is required to per day. Okay. So at this stage, for the design of the PV central, you have several choices. As I told you, you can design it for just answering to your energy need, or to answer to energy need and to be able also to charge the battery at the same time. Okay, so if you oversize the PV, it could do both, charge the battery and use the energy as when there is sun. Okay. So you have to size the battery capacity. Okay. So to size the battery capacity is quite simple. It is the energy that you need per day, and you have to choose how many days of autonomy you want. Okay. Is it 1 day, 2 days, 3 days, 4 days, 5 days? How you could choose that? How can you choose 1, 2, 3, 4, 1 week?
But the requirement will be very, very high in your place, so the sun is not there.
Yes, so you have, now there is a lot of web meteorological data. So for sure, you have to go on internet and have a look on the specificity of the local climate, summer and winter. In some area, for example, I imagine for the mousson, you will see that there is some days that there is no sun. So, of course, you will not take the whole period of the mousson, but investigate more locally what is the classical weather and how long you can have no sun. Of course, for example, in Europe, you can have 2 weeks without sun, so you will not put battery for 2 weeks because it will explode. But in some other country, you have enough sun, but you can see that sometimes or during 3 days there is no sun. So it's like this that you can guide yourself to select the autonomy. Okay. If it is also for a school or for a dwelling house. A school, for example, the weekend will not operate, so say, okay, we can take only 1 or 2 days of autonomy because the weekend are not included. There is not the night that is included also because if it is office building, you don't use too much electricity during the night, so the battery could be reduced. Okay. So many parameters that could help you to make a reasonable assumption regarding the number of days of autonomy. Then, so you go on the side of a PV array and select components. So module, inverter, battery, regulator, and so on and so on. Cable. Okay. It's like this that the tools are operating. Of course, each time you have to check the compatibility between the components. As I mentioned, the inverter has to be well designed relatively to the power of the central. If it is too oversized, of course it will operate, but the accuracy to track the maximum power will not be so good, so you will lose some energy, and it's worse if it is smaller than the capacity of the production, because as soon as the power will be over the capacity of the inverter, it will disconnect. So when when he is not finding a maximum power, it means he is disconnecting. So your PV central is not injecting electricity anymore. Okay, so the inverter is a key element. All are key elements, but what is very important is to be consistent between each power, each intensity, in order to be fully compatible. For example, the modules, the field of modules, if at the born of the field of modules you have 48 volts, at the born of the extremity of the battery rack you have to have 48 volts. Okay, don't add 24 with 48 and so on. Okay, so here you have, for example, electrical energy required, so EG per day, average radiation, performance ratio. We will see more deeply what is it, but it is the global efficiency of the PV central. So that means that you have, assuming that you have a good selection of the cable, so in order to avoid Joule effect loss, well sizing of your PV installation, battery efficiency, so of 80%. So it is related to the charge and discharge, 80% efficiency. Okay, so that means when you see 80%, that there is also a MPP tracker. The depth of discharge, so 80%. So that means I'm going at the maximum which is advised for using the battery. 80% of discharge, and the number of day of autonomy. So the battery capacity is energy required. So as I told you, usually we identify clearly the energy, but we measure a little bit, so by 20%, or as a first approach. Multiply by the number of days of autonomy, divided by the depth of discharge. That means divided by the efficiency of the depth of discharge is to measure the capacity. Okay, if we divide by the depth of discharge of 80%, that means that we measure the capacity. Then the PV peak power is the energy which is something which PC so the power peak is energy that you need divided by the performance ratio. So as I told you, performance ratio will focus more on it, but it is the global efficiency of the PV central. So you measure that, multiply by the efficiency of the battery, multiply by the irradiation. Okay. So take it because maybe I think there is an application after. I will ask you. So typically in Europe and in France, we will focus on the worst months, so winter months, where the daylight is smaller and when the weather is awful. To see the classical irradiation, okay? In some country where the irradiation is more or less constant, we can use the kind of mean annual irradiation as IGPG, okay? So for our installation, for example, in December, the days are shorter. We will choose an inclined plane of 60 degrees south. 4 days of off-grid system, 2 days for off-grid system with diesel generators. So that means if you don't want to invest on 1 week of battery, which is very expensive, you can combine with another source, okay? If there is so much day without sun, you will not increase the number of battery. You will try to combine with another generation. So that's what I was showing to you, autonomous combined with electrical generator, diesel generator, even if it's not so good. Could be wind, depending on the area where you are. And now, as I told you, even we are looking at, even if it is connected to a grid, there are more and more often the addition of battery. Not because there is a grid cut very often in France, but because the price of electricity can change, and when there is a important need, it is the case during winter because there is heating system that are using electricity. The price is higher, so if you had some battery, you can charge the battery when the price is low and use the battery when the price is higher. Okay, so the autonomy is still the same when you, but you can combine with other source of energy regeneration in order to reduce the battery. Why it is 60 degrees of inclined plane? Because during winter time, the sunrise, we will see that this afternoon, is lower in the sky. Okay, so the more vertical you are, the better you are producing during winter time. Okay, so 60 is quite very well inclined because we are focusing on winter time to produce as much as possible electricity. If it is grid connected, we don't care about the inclination. We want to produce as much as possible to inject on the grid and to win money. Okay, so we don't care. It's around more 30 to 40 degrees because we want also to produce a lot during summertime. Okay, but during summertime we don't need so much electricity that for autonomous it is critical to have electricity. Okay, so that is the reason why that the inclination of your PV panels is also depending of the use you have. So 60 degrees is not optimum for summertime, whereas the days are bigger, but the sun is higher in the sky, so it's not an optimal inclination. But for autonomous installation, what is critical is to produce when you need and when there is a weak amount of energy, so it is winter. So that is the reason why it is 60 degrees and not 30 or 40 like if it was connected to the grid. Okay, so for example here we have a system with a small house or in the alpine space, for example, where you have some light, some TV with when you switch off without completely switch off, so there's the power and the number of time it is used for per day. For example, for the light, you consider that you will use the light 5 hours. The TV, you will show the TV 2 hours, and it's not good to switch on, switch off only like this, because there is still a consumption of 10 watt during 22 hours. Usually when you install a solar installation, you be careful not to have such consumption. Okay. So here you will have 120 watt of power per day. What is interesting is the energy, and so the total energy will be 542 watt hour. Okay, so the electrical energy required per day, it is 542, and so the capacity, if you estimate that you will have 12 volt, okay, at the board of your installation, the capacity will be the energy divided by the voltage, and you have 45 ampere hour. Okay. The maximum power which is required is 120 watt. So the maximum of intensity is 120 watt divided by the voltage, and it gives you the maximum of the intensity. So you see, it is 10 ampere, which is important in continuous. So it is the reason why that the design of the cable is very important also. Don't put any cables. It's very important to design it very well also, because the intensity could be high, And so if the cable is not under design, it will hit a lot until they will have a fire or it will melt or could destroy. So the cable we don't think too much about. We are thinking about PV battery, but the cable is very important also. If you have the intensity, you are able to design your cable. Okay. And you have also the inverter to use it. It's okay. So usually we don't take directly the electrical energy required per day like this. We measure a little bit to be sure. Okay. Is this clear? So I am going in south of France, but I can ask you here in Guwahati for the exam, be careful. So the need per day of my installation is estimated at 4 kilowatt-hour per day. So that means per year it's 1,460 kilowatt-hour per year. The global irradiation in a plane which is at 60 degrees, so Nice latitude is around 40 degrees. So the global irradiation is 2.84 kilowatt-hour per square meter per day in December. Okay. And the scale of the year is 1,592 kilowatt-hour per square meter per year. I said that I want 4 days, so it's ambitious, 4 days of autonomy. The performance ratio of my global installation is 80%. So that means that I have my global efficiency is 80%. The battery efficiency is 80%. The mass discharge battery is 80%. It's classical data regarding the battery that we take. So 80% it is because there is a MPP tracker. So the battery capacity will be 4 days, okay, multiplied by 4 kilowatt-hour per day, divided by 0.8, so the efficiency. I come back here. Okay, energy required per day, number of days of autonomy divided the depth of the, not the efficiency, the depth of the discharge. Okay, and then after I have the peak power, which is energy required, divided by the performance ratio, the efficiency of the battery, and the irradiation per day. So capacity is 4 days with need of 4 kilowatt-hour per day divided by 0.8 charge use of the battery. I find 20 kilowatt-hour. So to reach 20 kilowatt-hour, as I told you, when I am in at the extremity of my PV central, it's 12, 24, it could be 36, could be 48. It's this kind of multiple of 12, okay? Usually a panel, at the bottom of the panel you have 12, 24, 48. So I can find that it could be 48 volt with a capacity of 416 ampere hour. Okay. For my peak power, so it is 4 the need divided by the performance ratio, 80%. There's almost everything is 80%. It's not easy to see. 80% of efficiency of the battery multiply by the global irradiation per day. Okay. So I will find in this configuration 2.2 kilowatt peak. Okay, so it's a small installation. I come back to my formula. So power peak is energy divided by the performance ratio, the efficiency of the battery, the irradiation per day. Usually, a conventional for a dwelling house connected to the grid, in France, you are not allowed to put under 3 kilowatt peak. Okay. So this is for autonomous installation. You do what you want. It is 2 kilowatt peak, but if it is grid connected in France, you are not allowed to go lower than 3 kilowatt peak. Okay, so the annual production used will be about 1,460 kWh per year. The photovoltaic generation will be 2.2 kilowatt peak multiplied by the mean global irradiation per year. So it's 1,592 kilowatt-hour per square meter per year, multiplied by the performance ratio. So you will generate 2,802 kilowatt-hour per year. Okay. Is it okay, or you have some question? So it is a roof design. Of course, you have also to identify if in the surrounding of your installation you have no shadow, okay? Because data that are provided on the global irradiation on the inclined plane of 60 degrees and the wool, the global energy received on this plane for the year, it is without shadow. So it's very important to be able to identify in your surrounding if you have a close shadow or mountainous area that could modify that. Okay. Regarding the standards, so for PV modules, you have a lot of different standards depending of the country. Each country gives some standard to be sure. It is necessary for the insurance to have some standards, because if one of the component is not referenced in a standards, it could have problem after if there's fire or problem of damage. So there is standard for PV modules, for inverter, for battery, for cables also. Cables is very important to take some cables dedicated for solar, because they are submitted to high intensity and also to UV because it's outdoor, and so they are aging very fastly. A part of important thing is LCA, so life cycle analysis. As I previously mentioned when I was speaking about the production of PV modules, there was some critics about the amount of energy which is necessary to produce PV panels. As I previously said, you have to use a furnace where you will generate the silicon. Okay, this furnace is over 1000 degrees to allow to melt the silicon. Then you have to cut. Then you have to treat. Then you have to put some silver, and then you have to put all the sails on the glass with resin. You have to heat again to make the resin encapsulate the so there was some criticism, and there is still some. So we have demonstrated that finally during his life, a PV modules produce more energy that is necessary to manufacture it. But there is still some critics, and it's justified about what we do after the life of the PV. Okay, is it possible to recover part of the material? We see, for example, that for the wafer is not possible because the silicon has been treated with bore and phosphor with anti-reflective coating. There is also some resin that is in the surrounding, so it's not so easy. So there is more and more study on life cycle analysis and recyclability of PV. So there is an European directive that push to recycle the PV and to recycle at least 80% of this panel. So it's not an easy task to recycle. To recycle don't mean to use it, to use the material for the same purpose, of course. So it's not to use the glass to rebuild some PV modules, to use cells to rebuild PV modules, and so on. So silicon, in terms of material resource, there is silicon on Earth, so it's not really a problem. Silver is more delicate. So silver is to collect the electron at the surface of a wafer. Okay, you have around 0.12 gram for watt peak for a panel. So you have some silver and could be expensive. It's becoming rare since 2021. You have some tellurium sometimes at a very low concentration. You have 0.01 ppm. But it is a rare earth. You have also some indium, also at very low concentration, but it is also considered as a rare earth. For the battery, so for lead, you have it's 70% of the battery on the market. Lead also is becoming rare. Lithium is rare also, is used everywhere. So the reserve is not so huge. So in terms of resource, is more delicate at the cell level regarding silver, and at the battery level regarding, yes, the main components of the materials. And it is more and more used for electrical car and so. You can have also, for some PV technology, cadmium, tellurium, arsenic of gallium, dangerous materials, of course, dangerous for environment. Silicon is not dangerous, but cadmium, tellurium, and arsenic of gallium is toxic materials. So regarding the energy payback, we have had a huge improvement, okay, compared to the beginning of the manufacture of PV panels, where the energy payback, so on the vertical axis, it is the number of years, okay. So you can see that in the middle of the 70s, the energy payback for the PV panels was around 20 years. So at that time, it means that yes, PV panels were producing just a bit more than the amount of energy that was used to manufacture. Why? Because the efficiency of the cell were very low, okay, and the process of manufacture the PV panels were closely the same as now, okay. Whereas now, since 2010, we have reached a very low level. The energy payback, due to the increase of efficiency of the cells, mainly that, the increase of efficiency of the cells, the energy payback time in number of years has considerably been reduced, and it is 1 or 2 years. Okay, after 1 or 2 years of operating, a PV panels reimburse the energy that has been required to manufacture it. Energy for which is necessary for manufacturing these PV modules, so classical monocrystalline or polycrystalline is around 500 kilowatt hour per square meter. Okay, so that means that for watt peak per watt peak, it is around 4 kilowatt hour per watt peak. The energy payback time is around 3 or 4 years. Okay. For amorphous silicon, it is shorter. It's 2 years, but the performance are less important. For cadmium tellurium, the energy which is required to manufacture is around 130 kilowatt hour per square meter, which is lower than classical silicon, and the energy payback time is around 1.3 years. Cadmium tellurium is quite efficient, but yes, there is some toxic materials, and it's a rare earth also, rare materials. So in terms of emission of CO2 for the different, if we compare, because if you want to make a life cycle analysis of solar PV, we have also to compare to the other way to produce. So emission of CO2 per kilowatt hour, which is produced by hydroelectricity, is 4 kilowatt hour per gram of CO2. For nuclear is 6. Okay. For wind, could be very large scale, between 3 to 22 emission of CO2 per kilowatt hour. And for photovoltaic is 60 to 150. Okay. Why such level? You can see it's not very good compared to hydroelectricity, nuclear. Hmm? No. Hmm? No.
Maybe France nuclear more focus is there because of the plants it is low.
No, yes, nuclear generate a low level of CO2 per kilowatt hour, but more than hydroelectricity. Why for photovoltaic it's higher than this kind of resource? Hmm?
Lifetime.
No, it's not lifetime.
Can you repeat the question?
The question is why to produce the equivalent of 1 kilowatt hour of photovoltaic, the CO2 content finally is between 60 to 150.
The glass layer puts more energy.
Whereas, no. So it's not.
Manufacturing of solar cells.
Yes, it is manufacturing. And why so high? Because it's manufactured mainly in China. And at that time, China is still using a lot of coal to generate electricity to then manufacture PV and PV panels. Okay, that means that the use of energy for PV module manufacture is very high in CO2 content because of the energy source which is used to manufacture them. Okay, if China continue to develop PV such as now, it's more than 80% of the production of the PV in the world is in China. If it was changing by using electricity from dam, nuclear, and wind turbine, for example, this weight of CO2 will decrease. Okay, but it is energy which is used to manufacture that is important, is very carbonate at that time, still carbonate. Okay. And then after you have use of classical other, which is carbonate, but because it is gas, petrol, and things. But
That's why I wrote 16 in Germany and 870 in China.
sorry. Sorry.
Average for countries in France is 90 gram,
Yes.
then 16 in Germany.
Yes. 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 That's yes. Yes, sorry, I did not say. So yes, in France, because it's mainly nuclear, so the content is lower. In Germany, because they were still using gas, but now I think it will decrease because there are more and more wind and solar energy. And in China is important due to the use of the back field resource, which is coal. Yeah. Okay. So, but this has to be included in the weight of the PV panels. As well, if you put a PV panel which has been manufactured in China, plus imported in Europe, there is a transportation also. Except if you are using hydrogen boat, for example, it will be also a cost in terms of CO2. So it's not, yes, so it's pushed to produce locally, to use locally, and to produce with clean energy, of course, because the content, otherwise the content, even if it's a green energy at the end, the content to produce it is not so good in terms of CO2. Okay. How to recycle it now? So there is different way. Okay. So this way, so you will have to take the panels, usually on the surrounding of the panels, you have a frame in aluminium. So you will take out the aluminium frame. So after you go to backsheet removal, then you go to EVA burning. So it's a problem because EVA is here to encapsulate the cells and to be fully waterproof during the lifetime of the PV panels. So EVA is everywhere. Okay, you put a slide of EVA, you have heated the EVA, and the EVA melt and encapsulate perfectly the PV cells. So even if you want to heat the PV panels to try to separate the backsheet and the cells, of course the EVA will become a kind of viscous element, but you will never have a clean surface of the glass, clean surface of the PV cells. You will separate, but you will have EVA everywhere. So the only way, if you want to recover the materials, is to burn it, or maybe to use, I don't know, acid or chemical reaction to dissolve the EVA. But at that time, it's going and it's burned. Okay. Then the glass and the cells are separate. Okay. And you can after recover the silicon cell fragment. The glass is also broken because the glass is I don't remember. We can trumpet glass. It's very strong glass that been specially manufactured to resist to shock. So it is a very hard glass. It has been specially treated for that. It's like for the car, okay? But if you have a strong impact that will destroy the glass, it will explode in multi-piece, okay? So you can't cut such a glass. You can't take this glass and say, I will cut to make another glass or things like this. It is specialized heated treated glass that is not cuttable and only destroyed in small pieces, like a car. So you will have small cullet of glass, and then you can, in the other side, recover all the metals, especially the silver. Okay. So it is a more clean way actually to recycle the PV. What is about the silicon cell fragment? You can't use it anymore for PV production. As I told you, there was too much treatment, chemical treatment, mixed with silver. So the purity, for sure, even if for PV manufacture you need less pure silicon, it's not usable for PV. Okay. So you have the percentage in terms of composition. You have 78% of glass, 10% of the aluminium, which is mainly for the frame of the PV, 7% of the plastic, so EVA, and 5% of metals and semiconductors. So it's very light. Silver is very light and silicon is very light. Do you have some remark for this? So I have one remark. It is to remove the frame is okay. To remove the backsheet is not so okay. You have to heat you have to heat the modules because you have glass, resin, cells, and backsheet. And the backsheet is glued with the resin. Okay, so if you want to separate the backsheet, which is generally a Tedlar, you have to heat a bit. Okay, it's less delicate to separate with the glass because it's Teflon. Sorry, because it's easy, but you have still to warm a bit. So here, to separate the backsheet, you have to warm. Then here, you have to burn, so that means you have consuming energy also. Okay, and to separate the glass, so you have to inject energy at least 2 stages to recover, to recycle it. So that means if you are considering the whole life cycle analysis, you have to include also in the energy payback time the manufacturer of PV, but also the recycling of the PV. This is a part of energy which is also included in the energy content. Okay. I've made something wrong or no? It's okay. I think it's not full screen, but okay. There is another way to recycling, which is not a real recycling. The other way is to take the panels, get rid of the aluminum frame, but then after to break it in a very small piece and to use it to as a underground layer for road, for example. Okay, for building some road, it is used as a kind of granular that is under, so it's to hide it. But it's not real recycling, but it's also the second way. This is more the complete recycling way. The other way is to break the PV panels in a small pieces and to use it for road construction. Or to put, we can put everything also in the concrete. There is some try to use it as a material of construction, okay. An interesting study showed that in urban area, when we want to massively integrate solar PV, in some country you can reach around 45% of the energy need, managing the production at the scale of a big territory, and in US more, only on building integration. And why in US more? Because a big house, there's a lot of availability in surface integration, and so this shows that. As I previously, and there was yesterday an interesting question. Okay, there is a lot of study to try to see how we can manage the production, maximum of production of energy where the energy needs are, so in the cities, and how to manage the flexibility of this. But there is also a study working on the impact of such a massive integration at the city scale on urban climate, and it's not still fully identified. What are parameters that are interesting? It is it's a mix between English and French. Energy yield ratio and energy payback ratio. So here you have some different technology, and so the energy payback is continuously decreasing because of the efficiency of the modules, but you have also yes, full screen. Yes, thank you. To consider the lifetime, okay. So here it is a study for 20 years of lifetime or 30 years of lifetime, and yes. So for the different technology, of course, the energy yield ratio is good for country like Australia. Northern Europe a little bit less, and depending of the way to integrate, is it grid connected rooftop system or is it solar home system, you have also different energy yield ratio. Okay, so it is yes, energy payback. So this is important also to consider in the life cycle analysis. So here, sorry, it is in French. For Paris, Lyon and Marseille, so Paris is in north of France, Lyon middle, and Marseille south. So the radiation are higher in Marseille per year than in Paris, than in Lyon. So you see, more you are going in the south, more the global irradiation is higher. There was some study if you integrate as a roof, so the toit, the facade, depending of these cities, and what could be expected. Of course, when you are integrate in a facade, you can see that, for example, for Paris, the energy payback time in terms of years is higher. If you integrate your PV central on a facade in Paris, the energy payback time will be around 4 years. Okay. Whereas if you integrate on the roof, the inclination is more optimized. You have around 3 years. But why the facades are studied? Because the facade in a city represents the more the biggest potential of integration of solar energy. When you have big tower, the roof is very limited compared to the facade. So the energy payback time is higher in terms of year than you are in facade. For Lyon, for example, when you integrate in a facade, you will have energy payback time 4 years. Whereas in a roof, it will be 2.6 years, and in Marseille, it could be interesting and very to use it as in a facade or on a roof. So you have 3 years of energy payback time when it is vertical, 80 degrees inclination, and around 2 when it is on the roof. Of course, so in the life cycle analysis, it depends of the way you integrate it to the building also. Okay. Do you have any question regarding this part? So this afternoon we will do a tutorial regarding the design of a PV central. You will work a bit, and now I just finished for the performance ratio. I spoke about the performance ratio on the design, so I will show you this. No, oui, je regardais là. Yes, to open a document. Performance assessment. Yes. Thank you. Oh. Okay, thank you. Okay, so usually the one thing which is important, it is when you are producing electricity, very often the classical curve of the production along the day is like this, like a Gaussian, okay? Why classically? Because we put at the south if we are in the north hemisphere, or in the north if we are in the south hemisphere, and we try to produce as much as possible. So that means the morning we start to produce, and at midday, at time solar through, we are producing the maximum. Now, and so that obliges for the other part to adapt, to answer when there is no sun, and to manage this overproduction compared to the need. Okay? So now, as I was previously said, that we are investigating to integrate on the facade, which is not optimal inclination, but also to integrate in east and west, okay, to better fit with the need and to have a better flexibility. Because in Europe, where now there is one turbine, solar energy, it's become more and more often a problem during summertime when it is very sunny day and windy day. There is too much production of electricity, and everybody try to give it to a neighbor. Germany, for example, sometimes inject in Slovakia. I was obliged because otherwise I was risking a blackout of my system. So you see that, okay, it was always led by the economic gain to produce as much as possible, but now we try also to produce when we need it. So east and west orientation have sense, because the morning, usually the people, when they are at home, they consume energy the morning, sometimes the midday when they come back, and the evening. Okay, so east and west have interest. So in more and more try to manage the flexibility at the scale of a big territory, saying that in a city we can admit that the morning some buildings are fully in the sun and will produce energy. Then after they will be in the shadow of the neighbor, but the other building will be in the sun and will produce energy. So you can imagine to have almost a constant production all over the day, playing with the variability of the sun at the city scale, even if some buildings start to produce and then stop. Okay, so at that time, of course, it is a concept, but it become more and more a reality regarding the flexibility of the grid. Okay. So I've already spoke about that, about the mismatch, but what is important, I want to show you. So this is a PV central which we are working a lot on. It is in Djibouti with one of my previous PhD students. We are investigating the production, the performance ratio, the impact of the soiling on the PV panels. Of course, there is some times where there is a lot of sun coming from the desert. There is some times where there is some rain. There is sometimes where there is some specific wind, which is, we are looking also at the impact of the wind on that, to identify classical performance ratio, but also other parameters that can modify the performance of the PV central.
Like people is there in the rooftop. The pebbles, small pebbles.
It's not on the rooftop, no?
It's the rooftop.
Ah, no, it's not a rooftop. It's a big central, not on a rooftop. You can see the building, so it's on the ground. And the inclination is very small because the latitude in Djibouti is around 10 degrees. Inclination is 10 degrees here. So it's very a problem for the dust because it's not horizontal but almost. So dust can stay long time, whereas when it is more inclined. And so there's many parameters that we are studying it. Okay, so for the performance assessment, so there is reference yield, so what is expected, okay, when you are designing your PV central, you are expecting a reference yield, but you are losing some energy due to the array, the cables. You have then the array yield, and you have over global loss, though that could be linked to the temperature, which is not well known at the time. It is a soiling. What is the soiling layer will impact very strongly the performance. So the main difference between what you expect and what you really have, okay, the ratio of that is a performance ratio. But finally, you can see that it is a kind of a global efficiency, okay. And it is a very interesting parameter. A good performance ratio. That means it's give an idea of the operating condition of your central to see if it is comfortable or not. So if the central is operating well, in a good condition, quite comfortable, it is 80%, okay? If you are under 80%, that means that there is a problem. A problem that you can resolve, or a problem which could be linked to environmental parameters, okay? Typically, temperature, okay? So if you are under 80%, if in principle when you look at your PV central, all the PV seems to be good, you can have a drone and have a view of infrared with an infrared camera, no hotspot, everything seems to be okay and so on. It is the temperature, because maybe it's too hot outside, and so under 80 is temperature. It could be linked also because the PV central is not well designed at the beginning. If you put on a roof, if the installer puts the PV panel directly on the insulation, for example, you will go at a higher level of temperature during summertime, and the performance ratio will decrease. Okay, so it's a way also to see if your central has been well installed, because between design and reality there's also the installation. Okay, and if you are all the time under 80%, there is a problem. If your panel seems to be okay, if, there is a problem. So it's a very good indicator of the health of the PV central. But also that means that this indicator is varying all the time, okay? And usually we analyze it per month. We estimate the performance ratio per month, that we will do that Friday. So do you think that the performance ratio is better in summer or in winter? No, is bad. Because the paradox is that during summertime, as the day are longer and the day are sunny, your central will produce more, for sure. Okay, but the performance ratio, when you compare to the winter, will be lower, will be worse than winter, because the temperature is higher. And so usually you will find that in summer you don't care about the performance ratio because your central is producing and so on. But when you look at the performance ratio, you will see that is worse. Whereas in winter, in winter, the main problem of the production is that the days are shorter. Whereas if the day was as long as in summer, the production will be much better because the performance ratio is better. You have also other indicators like reference yield. So the reference yield is the ratio between the solar radiation arriving at the surface and the quantity of the reference radiation. So it is, our reference radiation is 1000 watt per square meter. This parameter represents the number of hours during which the irradiation is equal to that of reference. Okay. In some countries, never reach. Okay. So it is. Does my central operate sometimes at the reference radiation? I remind you that the reference radiation is 1000 watt per square meter and reference temperature 25. Okay, so of course when it is lower than 1000, it will not produce what is expected when you are looking at the peak power. Okay. So this is an indicator. It could be in terms of hours. So it could be 0. It's not bad linked to the PV central. It is linked to the environment. Okay. You have also the array yield. So this is the PV is defined by the ratio between the total energy generated. So it's an energy. It's not a power anymore. By the PV arrays. For a defined period. So it could be day, month, year. And the nominal power of the array under standard conditions. So standard conditions is 1000 watt per square meter, 25 degree. And spectrum air mass 1.5. Okay. So it could be also in terms of hour. I suggest to have a month indicator. Because the year, if you have two different operating conditions between summer and winter, is reduced. It's better to reason between summer, winter, and months is good. We will see that for the performance ratio. You have also the final yield. So the final yield corresponds to the total energy produced by the PV system. So it's also energy divided by the nominal installed DC power, so in a power peak. This quantity represents the number of hours, so energy divided by power is time, of a PV array should operate at its rated power. Okay, so this normalizes the energy produced with respect to the size of the system. It gives you an idea if you have well-sized system or not, finally, okay? It's not so often used, but it's an indicator of the operating of your PV central. Well or bad could be linked to the PV central or could be linked to the environment, okay? That means a very polluted environment, very hot environment, no wind in the environment, some shadow, okay? Some shadow, if you have some shadow, it's not the fault of your PV central, it is the surrounding. Well, it may be the fault of the designer. And the performance ratio, yes, it's a global idea of the operating condition of the PV central, and also it could have some consequences on the design, on the installation of this PV central. This performance ratio also indicates the overall effect of loss. So it's included all kind of loss. Generally, we consider the inverter, the cable, the temperature effect, okay? But there is more effect that we try to integrate in the performance ratio. And as I told you, if it is around 80% or 0.8, it's good. No worries about your PV central. That means it's operating quite a convenable conditions, and it's good. If it is under all the time under 80%, there is a problem. Okay, 70% is a big problem. 75 is not good. So 75 could link only to the temperature. 70% that not only the temperature, there's something else. And if you are lower, that's a big trouble. Okay, even if you are producing electricity, it's important to see that. The system loss, of course, so it is different between the PV array yield and the final yield. Could be hours also. The capture loss, so the represent the loss due to the module temperature, the wiring, the cable, as I told, partial shading, spectral loss, soiling. So it's when you have a performance ratio which is under 80, under 75%, you should investigate this indicator to see what could be the reason. Is it in your PV central? And the array efficiency. So the array efficiency is the efficiency of the photovoltaic field, and it is the ratio between the total energy generated by the PV array to the amount of irradiation on the plane and the area of photovoltaic yields. So it gives you, yes, just focusing on the PV array like a PV panel, like a PV cell. Okay, just focusing on the PV. Well, there's other indicators. I will not go deeply on all these indicators, but it is all the indicators that we are using to identify the origin of a decrease of performance or abnormal performance that allow to give some indication. Okay, so the global data here. So you have solar radiation, the PV array. So the PV array is only the PV central. Then you have the inverter, you have the grid, and so at the beginning you have the reference yield. So then you have the array yield due to the efficiency of this PV central, and you have the final yield, and the global ratio between what you have at the end and what you have at the beginning give you the performance ratio, finally, which is integrating all of these parameters. If there is a bad performance ratio, that means that there is a problem on one stage of this. So after you go deeply in the different indicator to try to identify the origin of this bad performance ratio. Okay, we will in the application mainly focus on the global performance ratio, not on all these indicators, but it's good to know that performance ratio is a global estimation of the good or bad or comfort of our PV central. If there is a problem, you could investigate at each level the indicator to see where is the problem. Okay? It is the concept. Do you have any question on this? I think we can stop here. And then, so this afternoon is tutorial part. Maybe, I don't know how, well, no, I will, for the tutorial part, I will work on this. Okay?
Conclude here.
Yes?
So we'll next we'll meet at 3 o'clock. So please occupy before 10 minutes, so that we can start at 3 o'clock.
Okay.
For doing it takes time to complete the thing.
Yes.